This week in Fizzics TWIST.
We're trying something new. As climate change strengthens its grip on the world, an entire generation of kids are announcing to the powers that be that they're sick and tired of a lack of action, debates around alternative sources of energy are flaring up. Solar, wind, and hydro are renewable energy sources that have been proposed as alternatives to coal, but there is one option that doesn't seem to get as much attention: nuclear power. I think this is mostly because people are scared of nuclear power because of two very well-known nuclear disasters, the 1986 Chernobyl disaster and the 2011 Fukushima Daiichi disaster. The Fukushima disaster happened in Japan in 2011 after an earthquake and tsunami disabled the plant's power supply and cooling, melting its reactor cores and releasing ionizing radiation into the surrounding area. The Chernobyl disaster happened at a nuclear power plant in what is now Ukraine in 1986. During a safety test, an uncontrolled nuclear chain reaction was accidentally started, which caused a steam explosion and a huge fire that released radioactive contamination that then rained down over Europe, exposing potentially thousands of people to high doses of ionizing radiation.
Слово комментатору Александру Галкину.
Sounds scary, right? But hold on. Nuclear, chain reaction, radioactive, ionizing? What does any of this even mean? If, like me, your idea of what a nuclear power plant is comes from Homer Simpson wielding a glowing radioactive rod, then you might need a refresher on nuclear science. I decided to talk to someone who could bring me up to speed.
Yep, so my name's Bridget Murphy, and I am the Education Manager here at the ANSTO Discovery Centre.
ANSTO is the Australian Nuclear Science and Technology Organisation, which operates Australia's only nuclear reactor, based at Lucas Heights in New South Wales, and houses instruments called the Wombat, Platypus, and Echidna. Cute! What is nuclear science?
I'm going to give you an annoying answer. It's the science of nucleus. So you might know that the world is made up of atoms around us, tiny little particles, and in the very middle of those atoms we have a nucleus. So the very, very centre, it's very heavy. And so we study atoms, and we study the nucleus of those atoms.
Perfect. And what is the nucleus made of?
Well, it's made up of two little particles, protons and neutrons.
Atoms are the tiny building blocks from which all stuff is made. You can imagine atoms as being like a mini solar system. In the middle, like the sun, is our nucleus, which is made of protons and neutrons. Orbiting the nucleus like planets are electrons. Keep in mind there are other ways of visualising atoms. This is just one.
Yeah, well, you can even get tinier than an atom, but atoms are very small. And they make up the world around us. They make up the air that we breathe, they make up our bodies, they make up the objects that we use in everyday life. And these atoms are very small. If you pluck a hair out of your head, you can fit 1 million atoms across the width of a human hair.
Atoms join together to make molecules. For example, H2O molecules, which have 2 hydrogen atoms and 1 oxygen atom, make up water. But what is radiation? Radiation means anything that is released from the nucleus. As ANSTO describes it, a radioactive atom is unstable because it contains extra energy, or an unbalanced number of particles in its nucleus. Because of this, the atom will decay. Not like it completely falls apart, but as it loses energy, it changes type. For example, an atom of the element uranium decays into an atom of the element thorium. When this atom decays to a more stable atom, it releases the extra energy and/or particles as ionizing radiation. What is ionizing radiation? Ionizing radiation can strip an electron from its atom and can damage living tissues, making it quite dangerous. These are typically alpha particles, beta particles, or gamma rays. Alpha particles have 2 protons and 2 neutrons. If you look at the periodic table, you'll see that the element with 2 protons and 2 neutrons is helium, which means that an alpha particle is basically a helium nucleus. They can travel about 2 centimeters in air before being absorbed or stopped. Beta particles are either electrons, which are tiny negatively charged particles, or positrons, which are like electrons but positively charged. They can travel about 2 meters in air. Gamma rays are an electromagnetic wave, similar to visible light but with a lot more energy. But like I said, I think people are scared of radiation and nuclear science because they don't know what it means. I wanted to find out more. Is radiation harmful?
It can be. It depends how much there is and what type there is. But you have to remember that we are exposed to radiation all the time here on Earth. There's background radiation, you receive it from the sun, you receive it from the air that you breathe, it's in the food that you eat, and life has evolved in these conditions for millions and millions of years.
Perfect.
But yeah, too much radiation can be harmful. So we work really safely with radiation here. There are certain rules that we follow and principles that we follow to make sure that all of our workers here and the community as well aren't exposed to dangerous levels of radiation.
Cool. So by limiting time would be one way?
Yep.
And then what was the shielding, I think, is another way that you do it.
Yeah, that's right. Yep. So if you have something that's radioactive and you want to reduce your dose while you're around it, you can minimise your time that you're exposed to it. That's number one. You can place a shield in between yourself and the object to absorb some of that radiation. So that's 2. And the third thing is you can increase your distance. So if you can walk away from the object, that's the best thing. If you need to handle the object, perhaps you can keep it at arm's length from your body. So there are a couple of strategies that we use here at ANSTO. You can see on the table next to you, you actually have a container that we send out our medicines in, and this is for our main medicine that we produce here, technetium-99M. And we've cut through the container so you can see on the inside of it, and there's a big layer of grey stuff, that's lead. So we've got a whole lot of shielding around that medicine inside the container so it makes it safe for people to carry the container.
And it's really heavy.
It is very heavy,
Is that because it's very dense?
Yes. Yeah, lead's very dense, makes it a good shield of radiation. Doesn't mean that all shields of radiation are dense. For example, another shield of radiation is water. So if you look inside our reactor, it looks like a big, deep pool. And that water is for cooling as well as for shielding. So it means that neutrons from the core can't penetrate that water.
That's very clever. So radiation can be harmful, but organisations like ANSTO are able to massively reduce the danger by putting into place safety practices, like limiting time spent near radiation and by using shielding, like lead or water. So Homer Simpson tearing off his safety gear right at quitting time is not the best representation of how nuclear safety actually works. In nuclear power plants, neutrons collide with uranium atoms, cracking them open, releasing the neutrons inside the uranium atom, which then zoom off and collide with more uranium atoms, cracking them open, and so on, in a chain reaction. This is called fission. Imagine a bowling alley where the bowling ball and all the pins are neutrons. Once you've hit that first pin, the rest of them are coming down quick smart. This fission releases vast amounts of energy, which is used to heat water until it boils and turns into steam, which then spins turbines which power a generator and make electricity.
Across the world, there's probably 450 power reactors around the world and another 250 or so research reactors around the world. So there's lots of them everywhere else, but in Australia there's only one. And here's a question for you. Can you tell me how much electricity our reactor makes?
0.
That's right. Yes. So you come prepared.
I did know that one. So it turns out nuclear reactors aren't just for making electricity. Let's find out what else ANSTO does.
So the big things that ANSTO does are produce nuclear medicine for Australia and across the world. We irradiate silicon. So
For what?
for these are for electronics. So you might not know that silicon in its pure state is actually an insulator. It's not a semiconductor.
Right.
So we do something special to it to make it a semiconductor, and I'll get to that a little bit later on.
Sure.
And we also make these tiny little particles called neutrons. And once we get enough of those, and we make lots and lots of them, we can shine them through an object, through materials, and see inside them at the atomic scale, see where all the tiny, tiny little atoms are inside them. So, you know, that in itself are the big three things that we do. We also do a whole lot of environmental science too.
Really? Yeah. What type of environmental science?
Well, people don't really put the environment, the word environment and nuclear in the same sentence, but they really should. Mm-hmm. Because there's natural radioactivity all around us all the time that is safe because we're exposed to it all the time.
Yep.
And we can use these little radioactive atoms as like a barcode or a signature to tell us about the history of our environment and how it's changed over time. And so we have different instruments here, including, in fact, 4 linear particle accelerators that help us look at those atoms, count them, and see how things have changed in our environment over time and how we can better manage our environment.
So that's like dating.
Yep, that's right. Yep, we do carbon dating and other forms of dating on those machines.
Awesome. Wow, that's so much more than I thought. I thought that was just a big reactor.
Yeah, we're not just a reactor. We are certainly the home of Australia's only nuclear reactor, but that's not all.
Okay, we've learned a lot about nuclear science thanks to Bridget and ANSTO, but I think I'm lost. I don't know if I get it. I've never touched an electron or held a proton, never even seen an electricity. I'd like to have a better understanding of what nuclear power and radiation actually are, but I feel like I need a way to see this stuff for myself, to really understand it. And so, if I wanted to find out more about nuclear science for myself, doing some sort of experiment, what could I do?
Yeah, well, nuclear science, talking about radiation, it's tricky because radiation, you can't see it, hear it, taste it, feel it, touch it, that sort of thing. But you can make it visible using an experiment with the cloud chamber, and you can make this at home.
Awesome.
So you need to have a container where you can fill it with alcohol, so like rubbing alcohol, isopropanol. You might need something that's dark on the bottom of the chamber so that, because eventually you're going to get these little trails of radioactive particles that zoom through the chamber and leave like a trail that you'd see, in the sky from, say, a plane going through the sky. It sort of looks like that. And so you need a nice black background to be able to see that. And you need to make the bottom of your container really cold. And a couple of ways you could do that might be with dry ice or with liquid nitrogen.
If you have some.
Yep.
If you're lucky enough.
Yep. And at the top, you need to figure out how to make that nice and warm, because inside your chamber, you want to make there a big difference in between the bottom temperature and the top temperature, a temperature gradient. So one way you might make that top nice and warm is place a bowl of hot water up the top, okay? And so that temperature will go, that heat will be transferred through the top of the container. So if you can set that up inside a little bit of a tray, and make sure your alcohol, a few mil of alcohol is inside that container, leave it there for a little while, come back, and you might see some of these tiny, tiny little trails inside the container that you've got.
Which are electrons and muons and protons and neutrons.
Yep. Yeah, that's right. Yep. So you might probably see some alpha particles. They make nice, short, thick trails. And lots of beta particles, nice, long, thin trails. And if you're lucky, some protons and muons as well.
That would be awesome. Well, I think the cool thing about that is that it's not electronic in any way.
Yep.
It's just a container that fills up this evaporated thing. I think it's fantastic.
Yeah, it's so old-fashioned.
Yeah, it's great. Okay, plan. I think I understand more about this nuclear science thing now, but I still want to see it for myself. So I've decided to build my own nuclear reactor. No, not really. We're going to build a cloud chamber. Let's start with an aim. Our aim is to visualize nuclear radiation using a homemade particle detector called a cloud chamber. What's our hypothesis? What do we expect to happen? Well, honestly, I don't expect to see much. But ideally, we'll see a little alpha or beta particle. We should see short, thick trails for alpha particles. This is because those 2 protons and 2 neutrons make them relatively heavy. For beta particles, we'll see long, skinny, curly trails because they're tiny electrons that can be easily bounced around by the air. Let's get a materials list together. 1. We'll need a chamber. A clear plastic planter box will do. 2. We'll also need some isopropyl alcohol, or isopropanol. It's a bit different from the alcohol that grown-ups drink, but we still need to be careful with this stuff because it's flammable. You can get this from Bunnings or the chemist, but definitely get a grown-up for this. 3. We'll need a base. I'm going to use a metal baking tray. 2 of them actually, you'll see why later. 4. We'll need some black-coloured felt. This will absorb all the isopropyl alcohol, and the black colour makes it easier to see the trails. 5. I'll need a bowl for my hot water. 6. A torch to light the chamber since we're going to be turning all the lights off. 7. We need something to cool the chamber. I'm going to use liquid nitrogen because we always have some here at Fizzics. You could use dry ice, which is the solid form of carbon dioxide. You've got to be careful not to touch this stuff because it's super cold. If you're not a grown-up, definitely go get one to help with buying and building this if you're going to give it a go. Alright, let's go to the shops. Okay, I'm back. Got everything I need. Let's get building. Okay, I'm going to blue tack the felt to the bottom of the chamber. That's done. Now spray the isopropyl alcohol onto the felt. There we go. A bit more. It smells. Yuck. Now turn the chamber upside down so the felt is on the top of the inside. Put it onto my baking tray, and we're done. I'm actually going to add one more thing to my cloud chamber, which is something called tritium. Tritium is a radioactive material that glows ever so slightly. We've got it here at Fizzics because we use it in one of our workshops. It's in a little glass case, and it's perfectly safe. Because it's radioactive, maybe we'll see some particles coming out of it. I don't know. Now we just have to cool it down. For this, I'm actually going to place my oven tray inside of a larger, deeper oven tray and pour my liquid nitrogen in. This is where you'd use your dry ice. This stuff is almost minus 200 degrees C, so I'm going to use gloves and protective eyewear. Hear that noise? So that's the sound of the liquid nitrogen boiling and turning into gaseous nitrogen. I'm going to keep a window cracked so the whole room doesn't fill up with nitrogen, but it turns out that breathing all nitrogen and no oxygen isn't great if you like being alive, which I do. Now that's done, I'm going to fill my bowl with hot water and place it on top so we get that temperature gradient that Bridget mentioned. So let's go take a 10-minute break, see what happens when we get back. Okay, it's been 10 minutes. Let's see what we see. So remember, we should see short, fat trails for alpha particles, long, thin, curly ones for beta particles. So I'm going to shine the torch in. Nothing. I don't see anything. That's a dud. Nothing at all. So the isopropyl alcohol is definitely evaporating because I can see the mist, but I can't see any particle trails. Maybe it needs more cooling? So I'll pour some more liquid nitrogen in, and I'll get another bowl of maybe hotter water this time. And with that tritium, maybe the glass vial is blocking all the radiation coming out. So I don't know, I'll just leave it in just in case. And this time I'm going to tape around the bottom of the chamber where it meets the base. I'm kind of worried that the seal isn't very good. Maybe the vapor is leaking out. Well, I guess it's pretty rare to get the science right first time, right? Did Marie Curie grasp radiation upon first seeing uranium? No. Do you think Galileo nailed the telescope first try? Of course not. Was Isaac Newton smacked in the head by the theory of gravity? Well, that was a little bit different. Anyway, let's give it another 15 minutes. More liquid nitrogen. Whoa. That was cool. It worked. It worked. So I just saw this trail of vapor appear in the chamber. That was cool. I have no idea what type it was, though. Oh, there's another one. So that one looks too long to be an alpha particle, too straight to be a beta particle. I think we're going to need to do some more research. Okay, I think what we have is called a muon. This is what Bridget mentioned before. So muons are like electrons, but heavier. And get this, they're made from cosmic rays, like from space. Cosmic rays are like high-energy protons and atomic nuclei, that could come from the sun or even from distant galaxies. And they travel through space at near the speed of light, find their way to Earth, and then smash into a molecule in the upper atmosphere somewhere, creating this muon here, right here in the chamber. That's rad. Unexpected result. That's what science is all about, right? Now, I've been looking at this for a while. I'm not seeing any alpha or beta particles. No short and fat trails, no long and curly ones. Nothing. So honestly, I have no idea why. Another unexpected result. If you know why, message us on Instagram at Fizzics TWIST. Either way, we did manage to see the real-life effects of ionizing radiation. So, what have we learned? Well, we've learned what an atom is. Protons and neutrons in the nucleus, surrounded by a cloud of orbiting atoms. We've learned what nuclear science is, the study of that nucleus. And we've learned what radiation is, particles and waves that can be emitted from the nucleus as they decay. In our cloud chamber experiment, we learned it's pretty hard to get the science to work, so you have to persist and try new things. We learned that a muon is another type of particle that we can detect, that is produced from a cosmic ray from space, and that it leaves a long, fat trail because it's quite heavy. We learned that sometimes experiments don't go the way that you expect, and that's how science is done. If we always knew what was going to happen, we wouldn't learn anything new. More importantly, I think, is that we've learned that radiation is all around us always, and while it seems scary and weird, it's an incredibly important part of modern science and medicine, from irradiating silicon for electronics to medicine like technetium-99m. On average, 1 in 2 Australians will have a nuclear medicine procedure sometime during their life. And organisations like ANSTO utilise nuclear science in so many different areas, like materials science, biology, mining, engineering, and so on. It's also worth noting that if scientists stayed away from anything and everything dangerous, then no one would be getting anything done. Doing research well means understanding the dangers and minimising risk, whether that be wearing gloves while handling something super cold or properly shielding radioactive materials. But we started this podcast by talking about generating electricity. If we want to produce energy with the lowest negative health impacts, which source of energy should we choose? The answer is nuclear. Why? If you look at the negative health impacts of brown coal, oil, gas, biomass, and nuclear energy, nuclear is the lowest. So I found it really weird when Bridget told me
So, yeah, we don't produce any power. It's actually illegal by Australian law to make any electricity via nuclear means.
Wow.
So our reactor is for making medicines, irradiating silicon, and for making neutrons for research.
That's it.
Yep.
Why is it illegal?
I guess it's a historical question, really, than a scientific one, because power reactors do operate safely all over the world.
As you said, there's 450
Yeah.
in operation now.
Yep. And I guess the history of that is back in the 60s, when there was really quite the race amongst different countries across the world to make sure that they had a knowledge and expertise in nuclear science post-World War II, that people were starting to learn more about it, and people were starting to become concerned also about the potential negative effects of nuclear science and things like that. And in Australia, there was enough of a concern about a potential power reactor here that in the late 1960s, the Prime Minister decided, we'll put that in federal law, that we will never have a power reactor here.
Wow.
Yeah.
Never. And that's still not changed.
Yep.
That's a damn shame, if you ask me.
Yeah, well, it's in terms of ANSTO's opinion on it, we don't have an official one.
Okay.
Yeah, we do have lots of people.
You're just not in that business, so.
Yeah, that's right. We have people who have a lot of expertise who may have worked in power reactors before,
Yep.
but ANSTO doesn't have an official opinion on whether Australia should pursue nuclear power or not. There's certainly been a recent Senate inquiry about that with the federal government, and we were able to provide them with some expertise and knowledge about, what that would involve and things like that. But it's up to them to make their decision.
So there you have it. We learned a lot about nuclear science. That's it for this new format version of Fizzics Twist. Big thank you to Bridget Murphy and ANSTO for your time. And if you like this, let us know by chucking us a nice review. We hope to be making a few of these in the new year. See you then. Bye.